All right, well, as you can see, I'm starting to tape and it's already dark outside, so I'm having to use lights. It takes a long time to get these things uploaded and so on, so the day just got long with the other class on analysis. Anyway, what's written here on the upper side of the corner of the board, you may not be able to read, but it doesn't matter. It's just there to remind myself what is it that I set out to cover in the lecture. So we begin today with the issue of stochastic identification. Namely, there are many instances in practice, especially in civil engineering, where it is not possible to apply a load to the structure that you can actually have control over and measure it. Sort of like the one in the challenge problem and in the homeworks that we've done so far, where in order to do identification, we have to know not only the output, but the input also, right? There are many situations where we certainly can measure output, but we have to use excitation sources that are natural, meaning vibrations from the wind, vibrations from pedestrians, vibration from the traffic that is, in the nearby. In case of bridges, obviously from the traffic of the automobiles and so on. In other words, we need to use the vibration that is already there in the natural operation of the structure. So what we want to do is to see what can we do is all that we can measure is the output. So with that, we begin with the idea that, now this should be readable, that in discrete time, our model in state space is is x at k plus 1 is a discrete x at k, right? Plus what? If we knew the loading, it would be b discrete fk, right? But we don't know the loading. And whatever that loading is, we don't even know how it's spatially distributed. So what we say is, instead of saying bd times fk, let's just call it omega k, where omega k is just something, it's just a vector of the right size, right? Because it has to have the size of xk, but that's it. We don't know what it is. But we're going to make assumptions about the statistical nature of omega k, or wk. We also have the output, and the output is normally what? C discrete times xk, and it could have a d discrete times fk, right? Which we wouldn't know what it is. In addition to that, we assume that our output may also be contaminated by noise. That is, we cannot really measure the output exactly because our sensors are not precise. So the term that we put here, which is little vk, is intended to account for a possible d times fk, and if not, simply by the fact that we have some noise, so that what we measure is not really this, it's this minus something, right? Now, that is the system that we begin with to do a stochastic identification. So, when we do regular ID, we look for the matrices A, B, C, and D, right? In this particular case, it makes sense, it's obvious that we cannot set out, I'm trying to find my notes here, yeah, we cannot set out to calculate A, B, C, D because there is no B and there is no D. In other words, the matrices that have to do with the actual loading are undefined now. But what we can do is we can make some assumptions that will allow us to solve this particular problem as stated. And the assumption is that omega k is, how should I write it? Let me think. No. Okay, so that's the first assumption we make. This letter E means expectation. Expectation, in a loose sense, is mean, right? Mean. When we say expectation in probability, we just simply say what is the expected value, what is the mean value, what is it that you, in the average, expect to have. So if we take, let's say, to be clear, let's say that omega, let's say that this is the most, order 2 degrees of freedom, so that this was order 4, right? Displacement and velocities. So that means that omega would be 4 numbers at any given time, right? So omega times omega k transpose is like this. So that's going to give you a 4 by 4 matrix, right? So if you calculate that matrix at k equal to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1 million, 1 million and 1, 1 million and 2, and you take the average, then we are saying that the average of that matrix is Q, something, right? Now, if we take that matrix, omega k, right, times omega k plus 1. Where did I put the thing to erase? Hold it a second. Where is it? Here. Okay. So omega k times omega k transpose has an average which is Q. However, if we take omega, which is A, B, C, D, and we don't multiply it times its transpose, we multiply it times another omega that is shifted in time. So this is E, F, G, H, right? Where we are, this is omega, it's a vector, but I'm going to show it here like if it was a scalar. So we are taking something here at k and something here at k plus I, right? So we take the vector at k and the vector at k plus I. Take the vector at k here, like this. Take the vector at k plus I here horizontally. Multiply the two, get a matrix, right? Then move the k along the line and take the average of all that. What we argue, or not what we argue, we made the derivation under the premise that the only way that you get wk times wk to average to something is if you do it with no lag. But if you shift it, then this averages out to 0. Now, what does that physically mean? What it means physically is that W is a white noise vector. It's a purely noise, meaning that what happens in, let's see how I can explain this clearly. If you are here at k, there is a vector here A, B, C, D, right? If you are here at k plus 1, even 1 next to it, the idea is that the vector at k plus 1 has nothing to do with the vector at k. So here we get, P, Q, R, T, okay? This P has nothing to do with that A, or this Q with that B, or that R with that C, and so on, which is obviously not true if the loading were a sine, right? For example, if the load here had some pattern like this, then it's clear that if you have it at k plus 1, there is a relationship, right? It's just going to change a little bit, right? So the only way that k and k plus 1 are not related is if the loading, if the vector wk is changing in time fast in relation to the time step, so that you are here at k, and by the time you are here at k plus 1, this has nothing to do. Okay? That assumption of being uncorrelated in time, that is wk and wk plus 1 plus 2 plus 3 plus 4, being uncorrelated means that w, the vector w, is assumed to be white noise. Okay? So, wk transpose is q. It doesn't depend on k, right? If you just average, you just get q. Now, we also made the assumption that the noise vector vk is also white noise. And we call that expectation r. I will not write it, but you can hear me say it. The expected value of vk plus I is 0, except for I equal to 0. So these two vectors are white noise. Now, in practice, in reality, will they be white noise? No. In practice, in reality, they will not be white noise exactly, right? But what we want to say is that there are a large number of situations in practice in which the actual loading and the actual noise is such that the assumption that the vector is a white noise excitation and that the noise here is also white is not too bad. It's good enough to be able to do the to do the developments that we are going to do now. Okay? So that's our first premise, those two things. Now, we also have another assumption, or another number of assumptions, which will allow us to do the derivation. And that is that the state xk is uncorrelated with both of these noises. And that is necessarily true because white noise is not correlated with anything. So, well, actually I shouldn't say that. Wk is in fact correlated, perhaps you could argue, with xk plus 1, because whatever the value that there is here has something to do with xk plus 1. But what we're saying is that at k, xk has nothing to do with wk, right? Wk affects the next x, but not at k. The other thing is that the expected value of xk times vk transpose is also 0. Those are the four assumptions that we make with regards to these vectors and to their correlations with the state. And then our final one is not an, well, I guess it's not really an assumption, it's just the following. We assume that the state xk is stationary. By stationary we mean that the state xk is not that it is always the same, of course, is that its expectation is some matrix that doesn't depend on k. So if something is like this, if this was the state, of course the state is a vector, but if the state was like this, that means it only lasted from here to here, then obviously that's not true because the state here is 0, right? So the state average depends on whether I take it to here or all the way to there and so on. So what we are saying really is that when we are doing a stochastic identification, that is, there is not an applied load, we are actually looking at the system in operating mode. We have a system that is actually always responding to something, right? So this is the vibrations from the wind, the vibrations from the traffic, the vibrations from whatever, right? So there is no beginning and end, the system is just responding all the time, right? So we are just simply saying that the state at any k, whether you take it here, or you take it here, or you take it there, at k1 or k2 or k3, it's not that it is the same, it's that its expectation, what you expected that it would be in the average, is the same. Okay? Or actually, I shouldn't say its expectation. The expectation of x times x transpose is a matrix that does not depend on k. This is called stationarity. Okay? Clean a little bit here. Okay, so with those assumptions, then we just need to do some algebra and to derive what we want. So we begin, let's say this is equation 1 and this is equation 2. So we begin by looking at this. That is, since this is independent of k, then I can say that the expected value of xk plus 1 times xk plus 1 transpose is also equal to this, right? Because this is independent of k. And I can take my formula to find an expression for that. So what I would find is AD times xk plus omega k multiplied by the transpose of that, which is xk transpose AD transpose plus omega k transpose, right? From where you find, with a little bit of elementary multiplications, just 4 things, that sigma proves out to be AD, well actually let me just do the multiplications myself one time. So this is equal to AD xk, right, times xk transpose times AD transpose. That's the first term, right? Now, the next term, to save a little bit of writing, I'm going to make the arguments right here. So the next term is AD xk times omega k transpose, right? But the expected value of xk times omega k transpose is 0. So that means that the next term here in this multiplication is 0. If I now start with this one, I get omega k xk transpose AD transpose. And the expected value, because this I'm taking expectations all along, of omega k xk transpose is just the transpose of that, which is also 0. And so I'm just left with omega k transpose, and that is q. So what we have is that. Now, xk times xk transpose is itself sigma. And so we have developed the equation that says that sigma is equal to AD times sigma times AD transpose plus Q. Right? That is the first equation of the stochastic system identification approach. It says the covariance of the state, if we call this covariance, this XX transpose, the covariance of the state is equal to the transition matrix times the covariance of the state times the transpose of the transition matrix plus Q, where Q depends on the noise. Okay? Now, to continue, I'm going to need space, so I'm going to erase everything except this equation, right? Now our next thing is to look at, to define. This has nothing to do with frequency, this is just capital delta, or lambda, I'm sorry, capital lambda I is defined as the expected value of y at k plus I times y at k transpose. Now remember, y is the only thing that I have, right? Because I have output measurements. So we do have and can calculate empirically what is this thing. But now let's substitute. So we can say that lambda I, where I is how much I want to shift, right, is the expectation of, now what is yk plus 1? Yk plus 1 is going to be CD, right, times xk plus 1, plus I said 1 I think. It's going to be CD times xk plus I, right, times what? Plus vk plus I, right? That's the first thing. And then we're going to have to multiply it times yk, and yk is transpose, times yk transpose, and yk transpose is going to be what? Yk transpose is, from our formula, xk transpose, cd transpose, plus v, why did I say 1 here? I meant I. Vk transpose, right? So it looks like that. Now we move on and say delta I, lambda I, capital, is equal, so CD, right, times the expectation, because CD doesn't have an expectation, right? CD is just a constant matrix. But then these are the things that are stochastic. So I have the expectation of xk plus I times xk transpose times CD transpose, right? CD expectation. Actually, you know what? I think I could be clearer by just leaving the expectation outside first, so you can follow better. It just occurred to me, maybe I don't make any, let me just say delta lambda I is equal to expectation. I just leave this the same and just do the multiplication. So CD xk plus I times xk transpose times CD transpose. Then this term times Vk, the xk plus I, Vk are uncorrelated, and that goes away. Then the Vk plus I times this term, those things are, because this is white noise, uncorrelated. And so we have here Vk plus I times Vk transpose, and I can close the bracket. So that's really what we have at this point. Now, I'm going to have to erase here and bring it back. So otherwise I have no room. So we have that. Now, if I is not equal to 0, because if it is equal to 0, we have Vk transpose, and that was R, right? But if I is not equal to 0, then lambda I capital is equal, this cancels because we said this is white noise and it has no correlation for any shift. And we're only left with this part. Now CD are specific matrices, so the expectation operates only over the middle part. And so we have is CD times the expectation of xk plus I times xk transpose times CD transpose. If I is exactly equal to 0, then we have this 0 equals CD, the expectation of xk times xk transpose times CD transpose plus R, where R was previously defined as the expectation of VK transpose. So I guess I can erase here. Right? And then I can translate up here and put this 0 is equal to CD. Now the expected value of this is what we call sigma, and this is CD transpose plus R. So we get our first formula here, and then we get lambda capital I for a shift I to be CD times the expectation of the state shifted by I times the state transpose multiplied by CD transpose. Okay? Now, the next equation I debated whether to present the full derivation or not, but I think I will leave it as an exercise for those that may be interested in doing so. And I'll just say it is not difficult, but it's not trivial to show by looking at the original equation that the expected value of x at k plus I times x at k transpose is actually equal to AD to the I multiplied by sigma. That is a really important and interesting equation. It takes a few lines to get to it. I would encourage you to give it a try. It's not essential that you succeed, but you might want to entertain yourself seeing if you could derive this expression. Nothing fancy has to be done other than to use what we have already stated, but it's not immediately obvious perhaps. Now, the point now is to say, okay, if this is equation 1, and this is equation 2, and this is equation 3, then the point is to take equation 3 and to substitute it in equation 2. So then we say lambda capital shifted I, which we should remember is the expected value of the output. Actually, I should emphasize that. Remember, this is the expectation of the output at k plus I times the output at k transpose, right? So this is something we can calculate from, or estimate from the data, right? And that thing that we can estimate from the data is equal to this. And that is equal to CD. And instead of the expectation of xk plus I, xk transpose, I can put AD to the I times sigma, right? And then CD transpose. So this is starting to look really good, because now we can say the following. We can say that gamma, lambda I is equal, and write it like this: CD AD to the I minus 1 times, open a parenthesis, AD, obviously AD to the minus 1 times AD is just AD to the I, right? Times sigma times CD transpose, and close the parentheses and close that equation 5. Now look at that. What does that remind you of? Remember the formula for Markov parameters, right? The Markov parameters are equal to CD AD to the J minus 1 times BD. So we can say that something right here that we can calculate from the data, right, are actually Markov parameters for a system that has the C that we want, the A that we want, and a B equivalent, if you like, which is given by AD sigma CD transpose. This B equivalent may not mean anything right now, and actually it ended up, we don't really care in our fundamental applications, because what we really want is C and A. So the point is that if we are able to compute the covariance function, this is called the covariance function. If we can calculate the covariance function of the output for different lags, I equal to 1, 2, 3, 4, 5, 6, etc., we are actually obtaining things that look like Markov parameters for the first, second, third, fourth, etc. Markov parameter, right? For a system that has the C that we want, the A that we want, and some B. So even if we don't care about the B, we got the C and the A that we're looking for, right? I needed to say something else. No, not really. Our zero Markov parameter, of course, is not from here. Our zero Markov parameter, if we needed it, would be this, right? CD, sigma CD transpose R. And at this point right now, I don't recall, I'll make a mention next time if necessary, whether we have to make reference to it in the identification or not, because let's see if I recall correctly, when we form our Hankel matrix, no, we do not, right? When we do system ID, we form our Hankel matrices H0 and our Hankel matrices H1. And if I recall correctly, let me look here in the notes because I have the notes handy. Right. So when we form the matrix H0, the first entry in H0 is the Markov parameter Y1, right? And in the Hankel matrix H1, the first parameter that we need is Y2. So we really don't need the zero Markov, which would be this one right here. Therefore, let's see, now let me summarize how the procedure of system identification works in the case of stochastic loading. The only formula that matters for us right now is this one, right here. So, Actually, it doesn't matter, I'll erase it. So let's see what changes. In the standard ID, we begin with input and output, right? And our first step is to obtain observer Markov parameters, correct? Because we like a zip file, because those Markov parameters were kind of a mess to get otherwise, right? Then we unzip this observer Markov parameters and we obtain Markov parameters. This is on standard system ID. Now, in the case of a stochastic, which means with input unknown, a stochastic ID, we have nothing here, nothing here. We just go directly to here, and the Markov parameters are replaced by lambda I. Okay? So there is no input-output data. There is just, actually I should say, there is just output data. There is no observer Markov parameters in the middle, plus a procedure to extract Markov parameters. It's just that from the output, we obtain the covariance function of the output, and that is already what's going to be treated as if it were Markov parameters. This then, what is the next step that we do here? With those Markov parameters, we form the Hankel matrices H0 and H1. This is the same. And from those H0 and H1, we perform ERA to get A, B, C, D. Here, I mean A, B, C, basically, the D was the original. Here we do exactly the same thing. So the programs remain the same, except that the matrices that we extract, the CD is fine. The AD is fine. But the BD is not used later on, right? So we just extract these two things. So in a nutshell, that is basically a fundamental stochastic system identification scheme. In order for you to complete your ability to perform this, you need a program, you need to write a code that allows you, or you need a code that allows you to go from the output signals to the covariance function of the output, which are going to then be treated as if they were Markov parameters. I will post within tonight the program for you in Blackboard, which is going to be called stock or something like that, that does this computation. Therefore, you can immediately, using the same logic that you've used to do system ID in the normal way, perform system ID in the case where the input is not known. You just simply take the output, run the stock, treat what the output is as Markov parameters, and proceed in identical fashion, remembering that the BD is not going to be used, just your C and your A's. But it turns out that the C and the A is all you need to calculate the eigenvalues, which are the frequencies, and the dampings, and as we will see a little bit later today, also the eigenvectors. Okay? I'm also going to try to draft, maybe even tonight, if not tomorrow, a homework in which you can apply this scheme. I believe, if I am not incorrect, that I have given you in the prior problems inputs that are in white noise. Therefore, the output that we generate with those inputs satisfy the criteria that we need, so we could perform system ID on the output that we have without any changes. We could actually repeat the homeworks. and eliminate use of the input so that you could see the output. What would be the only issue that may not allow me to do that using the same data? The only issue may be that in a stochastic identification we are using expectations. So in order for something to have an accurate expectation, you need a very long time. You cannot, when the input is known, in fact, if there is no noise, you only need a very short time. I gave you sometimes, I think, 2,000 points, but I could have given you 500 or 300 and it would have been enough, okay? Because there was no noise. But in the case of a stochastic ID, where did I put the eraser? In the case of a stochastic ID, we are using the concept of expectation. And once we have expectations, accuracy demands that we have long signals. And so it may be that I will have to regenerate the output so that you will have sufficiently long signals to calculate the covariance functions of the output. Okay? All right. So you'll be able to try it and see. Now the next thing that I have for you to be able to do this stochastic ID is just a question of really just seeing how the program stock is run, which is very trivial because all you have to do is just tell it the input and how many Markov parameters you want to pull out, or equivalent to Markov parameters. So the next thing I want to talk a little bit about is using mode shapes in model updating. So far, in all your homeworks and in the model updating challenge, you've used only information from frequencies. So even when you do the identification, you calculated the frequencies, right? To calculate the frequencies, all you needed to do was what? To do the eigenvalue analysis of the A matrix. So once you had AD, right? Remember you went and you did a D to C and obtained AC, right? And then once you had AC, you calculate the eigenvalues of AC, and the eigenvalues of AC are the lambdas, right? Lambda 1, lambda 2, lambda 3, lambda 4, etc. that come in complex conjugate pairs and have the form minus frequency times damping ratio plus or minus the frequency damped times I, where the frequency damped is the undamped frequency times 1 minus the damping ratio squared, right? So you've only used this information. For updating. Now, we do not use, hardly ever, not to say never, the damping ratio because we really don't know the damping of our structure in a model and so on, so we don't normally want to update it. We just simply are interested in updating the stiffness matrix most of the time, because the mass matrix we also know with more or less sufficient precision. And that's what we've done so far. But what we might want to be able to use also, in addition to frequencies, are mode shapes. Now, how do we get the mode shapes of our structure once we have the A and the C? Well, to get the mode shapes, theoretically we have AC times phi is equal to phi times lambda. These are the mode shapes of the A, matrix. But the mode shapes of the structure at the point of the sensors actually, let me be more precise. Instead of saying mode shapes, let me say, it will help, I think, in the language. These are the eigenvectors of the A. But the mode shapes of the structure at the sensors are, let's say we call them phi, the product of the C matrix times these eigenvectors. Now let me stop the recording for a second part, because if it gets too long, it's an issue.